Hello and welcome to G Fun Facts Online, the show that unpacks the science behind our amazing world. Today, we're talking about a sound you're probably hearing more and more, the quiet, almost futuristic hum of an electric vehicle. It's the sound of progress, a cleaner future. But for all the sleek designs and instant acceleration, there's a bottleneck holding back the true electric revolution. It's the battery. The conventional lithium-ion battery in most EVs today is a marvel of engineering, but it's hitting a wall. It's like we've built a supercar, but we're still fueling it with a technology that's reaching its absolute limit. The problem lies in its very core, a liquid component called an electrolyte that's flammable and limits how much energy we can pack in and how fast we can charge. But what if we could change that? What if we could build a battery that's not just an improvement, but a complete game changer? That's what we're diving into today. The dawn of a new era in energy, the material science behind the solid-state battery revolution. Imagine this, an electric car that can drive over 1,200 kilometers. That's further than from Paris to Berlin on a single charge. And when it's time to refuel, you can do it in the time it takes to grab a coffee. This isn't science fiction. This is the promise of solid-state batteries. So how do we get there? The journey takes us deep into the world of material science, a world where scientists are designing new materials, atom by atom, to build the battery of the future. The secret, the absolute heart of the matter, is something called the solid electrolyte. In a regular battery, you have two electrodes, the anode and the cathode, and a liquid electrolyte that lets tiny charged particles, lithium ions, swim back and forth between them. To stop the electrodes from touching and causing a massive short circuit, there's a thin plastic sheet called a separator. A solid-state battery throws that whole design out the window. It replaces both the liquid electrolyte and the plastic separator with a single ultra-thin slice of solid material. This material has to be a superhero. It has to let lithium ions zip through it at incredible speeds for fast charging, but at the same time, it has to be a perfect electrical insulator to prevent the battery from shorting out. It needs to be tough enough to survive the manufacturing process and the stress of repeated charging, and it has to be chemically stable, not reacting with the powerful electrodes on either side of it. Finding a material that can do all of this is the holy grail of battery research, and it has led scientists to explore three main families of materials: polymers, oxides, and sulfides. Think of them as the three main contenders in a high-stakes race. First up, we have the polymers. These are the flexible friends of the solid-state world. Think of materials like polyethylene oxide, which is a kind of rubbery plastic. Their biggest advantage is that they are flexible and easy to manufacture. Their soft nature means they can stay in close contact with the electrodes, even as they swell and shrink during charging. The problem? At room temperature, they're a bit lazy. The lithium ions move through them too slowly for a high-performance EV. To get them up to speed, you have to heat the battery, usually to over 60 degrees Celsius, which adds complexity and wastes energy. So polymers are a good start, but not quite the final answer. Next in the ring are the oxides. These are inorganic ceramics, and their superpower is stability. Think of materials like the garnet-structured LLZO. These oxide electrolytes are incredibly strong, rigid, and stable. They are fantastic at blocking those pesky dendrites we'll talk about later, and they can handle the high-voltage materials needed for more powerful batteries. They are the bastion of stability. But their strength is also their weakness. Because they're so rigid and brittle, like a dinner plate, it's incredibly difficult to get them to make perfect contact with the electrodes. Any tiny gap creates a huge amount of resistance, slowing the battery down. To fuse them together properly requires baking them at very high temperatures, which is expensive and energy intensive. And finally, we have the sulfides. These are the high-conductivity hope, the potential superstars of the group. Materials like lithium phosphorus sulfide have an ionic conductivity that is shockingly high, sometimes even better than the liquids used in today's batteries. And they work great at room temperature. They're also relatively soft, so you can just press them together with the electrodes at room temperature to form great connections. So what's the catch? Well, sulfide electrolytes have a serious vulnerability. They are highly reactive with moisture. If they touch even a tiny bit of water vapor in the air, they can produce toxic hydrogen sulfide gas, the stuff that smells like rotten eggs. This means they have to be manufactured in extremely expensive, ultra-dry rooms, which makes scaling up production a major challenge. So we have the flexible but slow polymers, the stable but brittle oxides, and the fast but sensitive sulfides. The race is on to see which material can be tweaked and perfected first, or if a hybrid approach combining the best of all three will win out. But the electrolyte is only half the story. To truly revolutionize the battery, we also need to upgrade the anode, the part of the battery that stores the lithium when it's charged. For decades, we've used graphite, which is essentially the same stuff in your pencil. It's cheap and reliable, but it's bulky and can't hold that much energy. Solid-state electrolytes open the door to the ultimate anode material, pure lithium metal. Using a thin foil of lithium metal as the anode would be a monumental leap. It has a theoretical capacity almost 10 times higher than graphite. It's the key to making batteries much smaller, lighter, and more powerful. But for years, lithium metal has been seen as too dangerous for commercial batteries because of two major problems. The first is the dendrite menace. When you charge a battery with a lithium metal anode, the lithium doesn't always deposit in a nice, smooth layer. Instead, it can form sharp, needle-like structures called dendrites. In a liquid electrolyte, these dendrites can grow right through the separator, touch the other electrode, and cause a short circuit, leading to fires and explosions. Scientists hoped a solid electrolyte would act as an impenetrable wall, but it turns out dendrites are sneaky. They can still worm their way through tiny cracks or grain boundaries in the solid material. So researchers are now working on making stronger electrolytes and engineering the battery's interfaces to guide the lithium to deposit smoothly. The second major issue is the volume conundrum. Lithium metal physically expands as the battery charges and contracts as it discharges. This constant flexing can cause the lithium to lose contact with the solid electrolyte, creating dead zones that no longer work and cracking the delicate solid electrolyte layer. Given these huge hurdles with pure lithium, many companies are looking at a powerful alternative: silicon. Silicon is abundant, cheap, and like lithium metal, has a theoretical capacity about 10 times higher than graphite. But it has its own dramatic problem. When it absorbs lithium, it swells up to over 300% of its original size. Imagine a sponge that expands so violently it shatters itself into dust after just a few uses. That's what happens to silicon. To solve this, scientists are getting creative with nanotechnology. They're building silicon anodes out of tiny nanowires, nanotubes, or porous structures that have room to swell without breaking apart. They're also mixing silicon nanoparticles with a flexible carbon matrix that can hold everything together. These silicon-carbon composites are a very strong contender for the next generation of anodes. Now, we've talked about the electrolyte and the anode, but we can't forget the cathode. This is the positive electrode, and it's where the lithium ions live when the battery is discharged. For the most part, we can use the same high-energy cathode materials we use today, like NMC oxides. The biggest challenge here is, again, the interface. It's tough to maintain a perfect, seamless connection between the solid cathode particles and the solid electrolyte particles. Poor contact strangles the flow of ions and hurts performance. To fix this, scientists are developing special coatings for the cathode particles that act as a buffer, or creating composite cathodes where the electrolyte and cathode materials are mixed together like a perfectly blended cake, ensuring there's a path for ions to travel everywhere. The unique environment of a solid-state battery is also allowing for totally new cathode chemistries. For example, recent breakthroughs with a material called copper nitride have shown it could have more than double the capacity of today's cathodes, potentially enabling that 1,200-kilometer range we talked about. So, with all this incredible science, you might be asking, where is my solid-state battery? The answer lies in the manufacturing maze. Moving this technology from a pristine lab to a massive gigafactory is incredibly difficult and expensive. The high-temperature baking for oxides, the ultra-dry rooms for sulfides, and the challenge of producing massive, paper-thin, and absolutely flawless layers of these materials are all major hurdles. But progress is happening, and it's happening fast. Major automotive and battery companies are pouring billions of dollars into this technology. Companies like QuantumScape, Solid Power, Toyota, and Samsung are in a global race, and some are already starting up pilot production lines. The cost is high now, but forecasts predict that as manufacturing scales up, the price will fall dramatically, possibly becoming even cheaper than current lithium-ion batteries by the end of this decade. The solid-state battery revolution isn't just about one single discovery. It's the culmination of decades of research in materials, science, chemistry, and engineering. The road ahead is still challenging, but it represents a key that will unlock a more sustainable future. By giving us electric vehicles with longer ranges, lightning-fast charging, and superior safety, solid-state batteries will supercharge our transition away from fossil fuels. The revolution is well underway, being built right now, one atom at a time. Thanks for tuning in to G Fun Facts Online. Well, see you next time.